Right, the next question on capacitors is from June 2005, from A22 June 2005. Question 1a, define the capacitance of a capacitor. So capacitance is the charge stored per unit volt. You could also write down the equation, but you must explain what each symbol means, that Q is charge and V is voltage. B, part 1, a capacitor of capacitance 47 microfarads is charged by a battery of EMF 6 volts as shown in figure 1.1. Show that the charge on the 47 microfarad capacitor is 2.8 by 10 to the minus 4 coulombs. Just scan it a wee bit. So all you have to do there then is use your equation. C is equal to Q over V, but we're looking for Q, so Q is equal to CV, and that's 47 microfarads, and we know it's charged to 6 volts, and that gives you an answer of 2.82 by 10 to the minus 4. Now, in the question, everything's to two significant figures, so if I just round that up, and that's your answer there, 2.8 by 10 to the minus 4 coulombs. Calculate the energy stored in the charged capacitor. So again, another very straightforward question. So if we just use, we know, we can use any of our equations that we know, but I'm just going to use E is equal to a half CV squared. So it's a half. Capacitance is 47 by 10 to the minus 6. And that's multiplied by 6 squared. And that gives you an answer of 846 by 10 to the minus 6 joules, or 8 point. Again, to two significant figures, it would be 8.5 by 10 to the minus 4 joules. Okay, 8.4 by 10 to the minus 4 joules. Next part of the question, the charged 47 microfarad capacitor is then disconnected from the battery and connected to initially uncharged capacitor of capacitance as shown in figure 1.2. So this is now charged. It will act like a battery and it will share some of its charge with the second capacitor. They're in parallel, so you have to take that into account. It is noted the potential difference across the 47 microfarad capacitor falls to 4.1 volts as a result of this reconnection. So it initially was 6 volts and it's now fallen to 4.1. Calculate the capacitance, the value of the capacitance C. So we now know that V is equal to 4.1 volts. We can work out our total capacitance in this parallel bit of the circuit, which is the total charge divided by the voltage. Now the total charge stays as it was. It has just been shared with the second capacitor, and the total charge beforehand was 2.82 by 10 to the minus 4. Our new voltage is 4.1, and so therefore that gives us 68.78. I've written this in microfarads. Then we know that the total capacitance in in a parallel circuit, you just add them. So it's C plus 47. And C total is 68, and I round it up to 0.8 is equal to C plus 47. So C is equal to 68.8. C is equal to 68.8 minus 47, which gives you 21.7 roughly, 0.8. 21.8 microfarads. The total energy stored in the two capacitors after they have been connected is 5.8 by 10 to the minus 4 joules. This energy should be different from your answer to B1 part 2, and it was 8.5 by 10 to the minus 4 joules. Discuss whether this contradicts the principle of conservation of energy. So they're suggesting, has energy been lost? Or asking, has energy been lost? So, of course, there appears to be a difference in energy, and the difference in energy due to heat loss in the wires current flows to charge capacitor C. I might write it in there from the 47 microfarad capacitor. I would say something about the fact that it has gone down. So it seems to have gone from 8.5 by 10 to the minus 4 down to 5.8 by 10 to the minus 4. So say something about that, suggest that energy has been lost, and give a reason why you think energy has been lost. Heat in the wires. They've also suggested here in the mark scheme that there could be a spark whenever there's a connection, when two capacitors are connected. And that is possible. So that's a second option. So something about energy being lost and suggesting these two values here will get you 1 mark, and then an explanation will get you your second mark.